Okay, so in this video, we're going to be going over some ROC properties of the region of convergence of a Laplace transform. Okay, so we're not going to prove all these properties, but they're definitely good to be aware of. Okay, they're helpful for solving problems. Okay, so if we have some complex number A, so if A is a complex number, and if that is in the ROC of a Laplace transform, okay, then what can we say? Well, then, so is every other complex number S, such that the real part of S equals the real part of A. Okay, so what does this look like? How can you remember this? What is this really saying? It's just saying the entire vertical line containing A is in the ROC. Okay, so pretty much if I have, some little picture here of an ROC, if this is my A, then that means that every S that has the real part equal to that A, that entire vertical line, is also in the ROC. Okay? So if there's a complex number A that's in the ROC, then the entire vertical line containing it, that's all the numbers whose real part equals the real part of A, that's also in the ROC. All right, what else? What else do we know? Well, no poles can lie in the ROC. Okay, no poles can be in the ROC. And remember, what's a pole? A pole, the poles are just the values of S that make the magnitude, I think I mentioned this in a previous video, make the magnitude of a Laplace transform equal infinity. Okay, and for example, where it's going to play out for us mostly, these are roots, okay, places where a function equals 0, that's a root. Roots of the denominator of a rational Laplace transform, and I got to tell you what rational means. Okay, rational means that my Laplace transform x of s has some numerator and some denominator, okay, where these are both polynomials in S. So I'll show you some examples in a second. And actually, you've already seen examples, okay, because all of the Laplace transforms in our Laplace transforms pairs video, okay, were rational. Okay, if you look back, let me just give you some examples. Okay, 1 over S plus A. Okay, so would this be a rational Laplace transform? The answer is yes, because it is a polynomial in S in the numerator and the denominator, right? This is just S to the 0, and this is S plus A. Okay, so that's a rational Laplace transform. And all the Laplace transform pairs we're going to deal with in this class are rational, okay? And so where are the poles? Well, they're going to be the roots of the denominator. So we look at the denominator and say, what values of S make the denominator equal 0? And we can see that negative A is a pole here. Okay, I think I've pointed a lot of these out as we were going through them as well. Here's another example. 1 over S minus 3 squared. Again, that's a polynomial in S in the denominator and the numerator, so this is rational. And you can see what value of S makes the denominator 0. Well, 3. 3 is a pole. Okay, and one last example. What about 1 over S squared plus 1? Okay, again, it's a rational Laplace transform. It's a rational function, polynomial in S on the top and the bottom. Even if the top was, something like S plus 4 or whatever, that's still rational. The numerator is a polynomial. The denominator is a polynomial. Okay, and what are the poles here? Well, we need values of S that make this denominator 0. That would make the magnitude of this Laplace transform equal infinity. Okay, and you can see that plus or minus J are the poles here. Okay, so all the Laplace transforms we're going to deal with in this class are going to be rational functions. All the pairs that we looked at were rational functions. Okay, and so this is kind of the situation for what we're going to see in this class. Okay, next property. So more generally, If x of s is rational, so if the Laplace transform is rational, if it can be split up into a numerator and denominator, they're both polynomials, then its ROC is bounded by poles or extends to infinity. Okay, and let me show you what that means. We've already seen a lot of examples of this. These are just making these properties more precise. So for instance, if I had a pole maybe right there, okay, then what do I know? Well, first of all, I know that no poles can be in the ROC, okay, and if there were to be some value on this vertical line that was in the ROC, then I would get a contradiction because by property one, if there's a value that's in the ROC, then everything on that vertical line also is, but there's a pole on that vertical line. And so I know that nothing else on that vertical line can be in the ROC. That's where we draw the dotted line. And then, for example, the ROC could be everything on this side, right? It's bounded by a pole, by poles, or extends to infinity. So in this case, it's bounded by a pole on the left and extends to the infinity on the right. Or alternatively, what else could be the case if that was my pole? What else could the ROC look like? Right? Or I'll just do another example. What if my pole was down here? That's fine. I draw my dotted line and maybe the ROC is to the left. Okay, so that would be the left-sided situation, the anti-causal situation. This would be the causal situation. Okay, this is my ROC. So these are two options we've seen before. And also using these properties, we can ask what happens if there are two poles. And it turns out there are three possible options for the ROC with two poles. And pretty much this property is telling us what they are. I'll just draw the examples. Okay, let's say my poles are there and there. I can draw my dotted line. That'll be the first case. This will be the second case. And this will be the third case. Okay, and what are the three options? Well, pretty much it's just the three regions divided by these dotted lines, right? I have a region here, a region here, and a region here. And by these properties that we've listed, those are the only possible situations for our ROC. Okay, so option one is the ROC is to the left. Option two is the ROC is bounded by these poles in the middle. And option three is the ROC is to the right. Okay, and in this case, it's the left-sided situation. So this would be the anti-causal. All right, left-sided. Inverse Laplace transform we could take there. Okay, here it's a two-sided situation. I think we saw an example of that as well. Okay, it's not right side, it's not left side, it's a strip. Okay, so when you take the time function that had this Laplace transform with this ROC would be a two-sided function. And over here is the causal situation. This is right-sided. Okay, so these are the three situations for two poles, and you can imagine the general case, maybe I have a pole there, there, and so on, right? You can draw all these dotted lines, and then you have these possible regions, region 1, region 2, region 3, region 4, region 5. So there are actually 5 different time functions that could produce Laplace transforms that have these poles, but based on the specific region of convergence you get, whether it's, here or in between these and so on, okay, you could have a different time function corresponding to each of those 5 different regions. All right, so that's the general situation that we're going to see. Okay, and here's a question. Is it possible for the ROC to actually be empty? Is it possible that the ROC is the empty set, that the Laplace transform doesn't converge for any value of s? And that is possible. So let's see an example. So what does this function look like? Well, this function looks like this. When t is positive, I have an increasing exponential. When t is negative, okay, it would be a decreasing exponential, but now it's negative. So it looks something like that. It's flipped around. Okay, and let's try and take the Laplace transform of this. So what do we get? Well, if you think about it, right? When we take the Laplace transform of this, we're going to take an integral of that function, but we can split that integral up, and we're just going to get the sum of these two Laplace transforms. We're going to see this, or we saw this actually in the Laplace transform properties video. Okay, this is linearity of Laplace transform, but we already know these Laplace transforms. Okay, and if you recall, using the Laplace transform pairs, what we get is that the Laplace transform of this is 1 over s minus 1. Okay, we look at the coefficient there, which is 1, and the general form is e to the negative at, right? So a in this case would be -1. And so our Laplace transform is 1 over s plus a. So I get 1 over s minus 1. That's using a Laplace transform pair right now. And this one, using another Laplace transform pair, is 1 over s plus 1. And we know the ROCs in both cases. This is when the real part of s is greater than 1. This is when the real part of s is less than -1. And we need those s values, okay, we need both of these situations to be true in order to get convergence. We need both of these Laplace transforms to converge. Okay, so we need both of these for convergence. And we need both of them for convergence. So in other words, right, where's the pole here? It's when s equals 1. And the real part of s is greater than 1. We need that to be true, and we need our s value. We need our s value to be in that ROC, and we need our s value to be in this other ROC. The pole here is at -1. And the real part of s has to be less than -1. But wait a second, how can a point S be in this region and also in this region? Those two regions are disjoint. They have no intersection. Okay, but the intersection of these sets is empty. In other words, that is, there is no complex number S such that the real part of S is greater than 1 and the real part of S is less than -1, right? I mean, there's no real number that's greater than 1 and less than -1 at the same time. So there's no complex number whose real part can satisfy that as well. What does that mean? That means our ROC in this case is actually the empty set. That's our symbol for the empty set. Okay. The ROC is empty. This Laplace transform doesn't converge for any value of S. And so the Laplace transform doesn't exist. Doesn't converge anywhere. Doesn't exist for this function. Can't take the Laplace transform. Okay, it just diverges everywhere. It doesn't converge anywhere. Okay, so that answers that question. Is it possible for the ROC to be empty? That's a good thing to be aware of. And then all these other ROC properties are also useful, especially this one here for identifying what the regions of convergence could be based on the poles. Okay, so that's all I had for this video, and I'll see you in the next one.